In the second slide, I try to analyze the effects of cell phase modulation alone, while I assume there is no group delay dispersion. So big D is 0. So only focus on the impacts of cell phase modulation. And I did very similar things. The horizontal axis means the SPM coefficient, okay? But you know SPM is always positive. So not like the previous case. Previously, I need to analyze negative 0 to positive dispersion, GDD. Here, starting with 0, okay? There is no negative SPM. So the horizontal axes are the same. As you move to the right, SPM is stronger and stronger. Vertical axes are the same as before. The first one is about pulse width. Second one is about bandwidth. Third one is about chirp rate. Okay, so what have you seen? Very clear information. As cell phase modulation coefficient increases, your pulse width narrowing is weaker than the bandwidth broadening, leading to increased upchirp. Okay, so qualitatively, as SPM is stronger, your pulse duration is reduced, say from 330 femtosecond down to 260 femtosecond, if you have SPM. Okay, and your bandwidth is increased from here to here, but the factors are different. Pulse width compression is a factor of 1.3, but bandwidth broadening is a factor of 2. So bandwidth broadening is stronger than the pulse width narrowing. And the reason is now you have extra upchirp due to cell phase modulation. Okay. 所以类似的这个逻辑分析嘛，就是本来我的频宽如果增加2倍，我预期脉冲可以压缩2倍啊，不止压缩1.3倍。那为什么没有压得那么好？原因就是你的 steady state pulse 现在有因为 SPM 产生的 upchirp， 这个 upchirp 会 broaden your pulse. Okay. But simple information here is SPM might be good for generating shorter pulses, right? You got shorter pulse width, broader bandwidth. They are positive things. While group delay dispersion is different. Group delay dispersion is not good for short pulse generation. Right? Whenever you have group delay dispersion, pulse width is broader, bandwidth is narrower, so it's negative. 所以简单的结论是这样啊 ，SPM 可能是有利的 ，GDD 可能是不利的。Okay. Now, what happens when we turn on both knobs simultaneously? Okay, we have GDD, we have SPM simultaneously, but the sign of GDD is very important. Here we start with normal GDD. Okay, and qualitatively, both normal dispersion and the cell phase modulation cause upchirp. So they are actually sort of enhanced with each other, giving you strong, very strong upchirp. Okay. So here are the simulation results. Okay, each one. Only right half is plotted because right half means normal dispersion. We will see the left half later, okay, anomalous dispersion. And in each figure, you can see two curves. The blue dashed one means the previous case, only GDD but no cell phase modulation for comparison. This is a reference curve. The red one is you have GDD, normal GDD, but you have also cell phase modulation. So we have to compare with the red curve and the blue curve to see the impact of the interplay between normal dispersion and cell phase modulation. So what information could we have? As GDD is more and more normal, okay, D coefficient is bigger and bigger, your pulse gets broader, right? 你可以看到，越往右边脉冲都是变宽的。bandwidth 越往右边脉冲都会变频宽都会变窄，然后你的 upchirp 呢也会增加 ，OK。所以这个趋势是不管你有没有 SPM， 趋势大致都一样，但是程度不同，谁比较严重？红色的 curve 比较严重嘛 ，right？For example, your pulse width increases more seriously than the blue one when there is no SPM. Your bandwidth reduction relatively similar, not like this case. And your chirp rate increases more seriously when you have SPM. But this is consistent with our intuition, right? As I mentioned in the beginning, both normal GVD and SPM cause upchirp. So you got even stronger upchirp if both mechanisms play together. 所以我坦白说，这个结果也不 surprising， 也在预期之中，很合理，对不对 ？But when we change the sign of dispersion, things are very different. Now we have anomalous GDD and the cell phase modulation. Fundamentally, anomalous dispersion causes downchirp, while cell phase modulation causes upchirp. They are in conflict with each other. Okay, so they are counteracting forces. Some balance could be reached. So these are the simulation results. Let's pay attention to the left half. Okay, they belong to anomalous dispersion. Okay, so you can see the first blue curve is about pulse width evolution. As your anomalous GDD is more and more serious, your pulse width is broader and broader as expectation. The problem is, compare with the right half, the pulse width increase is less serious compared with normal dispersion case. So this curve is very asymmetric. 所以简单的说，我引入相同量的 GDD， 如果它是 normal dispersion， 那脉冲展宽的程度要比我引入的是 anomalous dispersion 还要严重。这边的展宽没有那么明显，另外一边的展宽是非常明显的。OK， bandwidth evolution is roughly symmetric。OK， 左右是不对称，但是没有那么严重的差别。Now, how about the chirp rate? Okay, as you can see, when your anomalous dispersion is more and more stronger, your chirp rate parameter beta is more and more positive. That means downchirp. Downchirp is more and more serious. But compare with the normal dispersion section, you can see the curve is relatively flat compared with the right half. So that means chirp rate does not change a lot as you increase your anomalous dispersion compared with increasing your normal dispersion. Okay. And these can be justified by the first sentence, since these two forces counteracting with each other. They can be sort of balanced. Okay. And if you still remember, in chapter lesson 3, we talk about solitone, right? Solitone is an extreme case when the two forces precisely balance with each other. You got solitone. Here, it's not precisely balanced, but the characteristics are already there. I briefly show you an even striking result. Effects of anomalous GDD and self-amplitude modulation, not self-phase modulation. Okay. So here, the three horizontal axes are about SAM, not SPM. This is amplitude modulation. The pulse shortening effect we expect from SAM, right? If it is normal dispersion, they are quite intuitive. But if it is anomalous dispersion, you can see a very different story. As you can see, if the curve moves to the left, that means your anomalous dispersion is stronger and stronger. But you see, no matter what is your SAM coefficient, the blue one means 1 unit. The red one means SAM coefficient is increased by 15%, 1.15. But you got almost the same result. Same thing in the bandwidth evolution and the chirp rate evolution. So simply speaking, the red and the blue curves almost overlap with each other in the left-hand side. What is the meaning of overlapping of two curves? It means SAM coefficient is unimportant for steady-state solution. So you have, although your SAM coefficients differ by 15%, you got almost the same, essentially the same result. So SAM is insensitive to the steady state. But it's very strange, right? Supposedly, post-shortening comes from SAM. If you have a stronger SAM coefficient, you are expected to get shorter and stronger pulse. But the reality is not like that. Even you increase the post-shortening effect, you still got the same steady-state pulse. You see the pulse width overlap, so no difference. Chirp rate overlap, no difference. So logically, it implies SAM is no longer the major force in pulse formation in this case. But for a normal dispersion case, you can see the two curves are separated. That means SAM coefficient plays important role in normal dispersion plus SPM, SAM. So I will talk more details next time, but a simple impression for you is, okay, sometimes steady-state pulse does not depend on the post-shortening effect. It depends on other things. Okay.